Problem 8 gave you a graph, pretty similar to this one. So you had some points, the points in red here obviously, and a curve that represents in some sense a best fit to that point. Now, the meaning of the graph, and you constructed a graph of this nature, you had pairs of lines. You were to measure or to estimate the length of the top line as a percent of the bottom. In this case, it looks like that top one is about 60%. Okay, so the top one is about 60% of the bottom one. And here the top one is more than 100% of the bottom one. Okay, so you know that extra there looks like it's 50 or 60% of the bottom one. So I'm going to say this one is, I think it's closer to 160, but let's just say 150%. Now, another thing we did was, having made these estimates and done it for about a dozen pairs of lines or so, without referring to the estimates that you made, you then estimated the bottom as a percent of the top. So in this case, if you estimate the bottom as a percent of the top, well, that looks like about 170%. And down here, it looks like about, I'm saying about 70%. Okay? So, again, these estimates need to be done without reference to these estimates, because these estimates could easily influence these. However, this would give us 2 points on this graph. It would give us 60%, that might be about here, 170% might be about here. So that would be a point, along about here on the graph. 60 here, 170 here. Okay? And it might be on the curve, and it might just be close to the curve. 150, 70, well, we come over here to 150, and we would come up here to 70, which would be about here, so that would be pretty close to the curve as well. Well, that's what we're estimating. Now, the first question was that you were asked to relabel these as ratios. The ratios would be, instead of 60%, well, 60% means there's a ratio of 0.6. The ratio of the top to the bottom is 0.6. Here the ratio would be 1.7. Here the ratio would be 1.5. Here it would be 0.7. So I can relabel this graph according to those ratios. 100% means a ratio of 1. It would mean the two lines are identical. So I can do a relabeling with 1 here. 400 would be 4, 200 would be 2, 300 would be 3. So up here I could do the same, 1, 2, 3. You're going to have trouble getting 4 in there. Let's try this. That's kind of bad. There's a screw right there. Had to write around it. So I apologize for the quality of that 4. Okay, so now the graph can be read. This point here looks like it's a little over 100 here, a little under 100 here. So maybe 95, 107 or something like that. Okay, so that's relabeled. Now, the other thing we asked to do is find the average squared deviation of these points from the curve. So what do we mean by that? Well, the deviation, you're told, is the vertical distance between the point and the curve. So the deviation, and let me do deviations in a different color here. So that segment there would represent the deviation of this point from the curve. You'd have a pretty short segment here, slightly longer segment here, here, somewhat longer here. Now these 2 points are going to give you pretty long segments. If I take this point and raise it up to the graph, it appears to intercept about there. This segment probably comes all the way down to here. So these orange segments represent the deviations. And I think I actually kind of aimed this one over too far that way. It's probably even bigger than what I drew, the one to the leftmost of these orange segments, but just for illustration, we're going to estimate these deviations. So, well, you should look at the graph. On the green scale or on the white scale, doesn't matter. What's this deviation? What's this one? What's this one? Okay, so let's just look at this one. What do you think that deviation is on the green scale, or what would it be on the white scale? Well, this segment is this long. It's clearly shorter than 100. Looks like it might be about 25. Or, and I'll use green to write equivalent, 0.25. Okay, so there's a deviation. Now, what do you estimate the rest of these deviations are? I'm going to make my estimates, and I'm just going to do them in green, just to not clutter up the picture any more than necessary. Make your own estimates. Okay, I don't think what I've got here constitutes a lot of great estimates, but still give us the idea. This is the biggest. This is over 100%, which would be probably 120% in this case. So that's a 1.2. This will be a 0.8. It's somewhat less than 100. This one was 0.25, so I'm estimating all three of these to be about 0.15, and this one being slightly shorter than those, about 0.10. So those are the deviations. Now, you were asked for the sum of the squared deviations. Okay, so we can list our deviations, but of course the question asked for the mean of the squared deviations. So having done the deviations, we square them all. And the squares are simple. 0.8, 8 times 8 is 64. That gives us 0.64. 1.2 gives us 1.44 when we square it, and the other squares are as I've written them. Now, one thing we can see from these squares is that these two are very dominant. All the rest of these add up to much less than either of these. Matter of fact, all these together add up to something just a little more than 0.1, which is only about 1/6 of the smaller of these two. So when you add all these together, you get not much more than the sum of these, okay? So you're going to get something on the order, when you add them all up and divide by the 7, you're going to get something on the order of 0.3 for the mean squared deviation. Now that would answer the question, but why would we want to ask a question like this? Well, it's simply that your best fit curve is the one that minimizes the mean squared deviation. Now, you can think about what would happen if we shifted this curve a little bit left or right. Okay, a little bit left or right. If we shift it a little bit to the right, we could probably increase this number to 2, decrease this one to 1. And that might, in fact, decrease, it would decrease the sum of the squares of these two numbers, if that's what really happened. Okay, so instead of getting 2.08 here, if these are both 1s, we would get 2. It might be that shifting it up or down would help. Okay, if we shift it up a little bit, we're going to decrease these three numbers, this one, and this one, because all these points lie above the curve, so we're going to decrease the deviation, but then we're going to increase these two. And that might well offset the decrease that we get for these two. It's not going to have a huge effect up here, though, and it's not going to have a huge effect anyway, because these two numbers, these two deviations, are still going to be really dominant. So that in finding the curve that best fits the most important points, if the deviation is to be the vertical distance between the curve and the point, these points are going to have a disproportionate effect on that deviation. And the point of my talking about that is simply to give you a little better understanding of what we mean by curve fit and an average deviation from a curve and the fact that we're trying to minimize that average deviation. Now another question follows. What's the y ratio when x doubles? Well, we should be on familiar ground here. We can choose an x value. Now I like to choose an x value out here so that we can cut that value in half. I'm thinking that if we're about here, we're about as close to one point as to the other. So I'm going to say half of that x value should be about here. Half of that x value should be about here. Half of that should be about here. Half of that should be about here, but it's going to be pretty hard to match up the graph point with this, and we'd be subject to a lot of potential error in doing so for reasons that I'm not going to necessarily comment on. Okay, well, if we look at the corresponding y values, okay, if we come straight up from this point, we come over to here. Here's a y value. Notice, incidentally, I'm not putting numbers in any of these. I'm just merely marking points. So I get this sequence of points. Now, x doubles from here to here. What happens to the value of the function? It goes from here to here. Now, it doesn't look like it doubles. Matter of fact, it goes from here to here. It doesn't look like it cuts quite in half. It looks like it goes down to about 70%. From here to here, it looks like it goes down to about 60%. From here to here, it looks like it goes down to maybe 30%. So we don't appear on this graph to get a really consistent ratio of our x values, our y values, when our x values double. Now I've gone ahead and labeled the x values x1, x2, x3, x4, the y values y1, y2, y3, y4. The x ratios, x2 over x1 equals x3 over x2 approximately, which is approximately equal to x4 over x3, which is approximately 2, as best I could manage it by drawing it freehand. The y ratios appear to be y2 over y1 looks like it's about 0.7, y3 over y2 about 0.6, and y4 over y3 about 0.3. There's no apparent constant ratio. Well, that's largely because this is a hand-drawn graph. If you do this using the graph on the test, you will find that the y ratios are pretty consistent at about 0.5. Now you can see problem 1 for a more detailed explanation, but same idea here. Y equals ax to the p, as will be the case anytime doubling x gives you a constant y ratio. So that y2 over y1 would equal x2 over x1 raised to the p. If x2 over x1 equals 2 and y2 over y1 equals 0.5, then we have 0.5 equals 2 to the p. 0.5 is the negative 1 power of 2, so that p would be negative 1. You wouldn't need logarithms to figure that one out, though you might need logarithms or good trial and error if you had an estimate other than 0.5, which you might well have. Now we can find the value of a corresponding to this graph. It looks like 100, 100 is pretty close to a point on this curve. So let's just say y equals 100 when x equals 100. Y equals ax to the p, p is negative 1, so y is ax to the negative 1. Plugging in 100 for y and 100 for x, we get this equation, which we easily solve to get a equals 10,000. If we use the green scale, and I probably should have done this in green, but if y equals 1 when x equals 1, then if a is then it follows by the same procedure. We go through the details that we get a equals 1, so that y equals ax to the negative 1 would be 1x to the negative 1, y equals 1 over x. In this case, if we're measuring in percents, y would be 10,000 over x. For the graph linear text, this is the best fit. compare.